Hello, everybody. I'm here to welcome you all to EarthShift Global's first Brown Bag webinar of the year 2023. And a very special welcome to Professor Boulay, who's an assistant professor at Polytechnique Montreal and co-directs the International Life Cycle Consortium of the CIRAIG, an international research partnership between Polytechnique Montreal, Canada, EPFL, and HES-SO in Switzerland. She coordinated the WULCA working group to build consensus into achieving a harmonized method for assessing water use in LCA and is a co-founder and co-chair of the MarILCA Marine Impacts in LCA, international working group supported by the UNEP Life Cycle Initiative and FSLCI, leading the development of metrics to assess impacts for plastic emissions in the environment. Please send your questions through the chat, and then we answer them for you at the end. Welcome, Professor Boulay.
Thank you very much. Thank you for the introduction, and I apologize for all these acronyms. Hello, everyone. Thank you for joining this webinar today, where it will be my pleasure to present you the latest development that we've done within the MarILCA working group, specifically with our team here at CIRAIG Polytechnique Montreal. So my name is Anne-Marie Boulay, as was already introduced, and I'm a professor there at Polytechnique Montreal within the Chemical Engineering Department. So we'll be talking about plastics today, and it probably comes at no surprise to you that there's been plastic bans, single-use plastic bans coming up all over the world, in European Union, Canada, India. And the goal is to ban these single-use plastic items, which often leads to the development of other types of single-use items made of other materials. Yet the LCAs, some of the LCAs that we have, don't seem to point towards higher environmental benefit of these plastic alternatives to single-use packaging or containers in this case. So these are just two examples. The one on the bottom right here shows you different indicators comparing chocolate wrappers for one in polypropylene, one in cardboard, one in paper. And the polypropylene one actually seems to be the one that performs best in all the indicators that are shown there. And the one on the left here, and we'll be coming back to this case study here on the left towards the end of the presentation. But this one looked at 3 different food containers, one of expanded polystyrene compared to one of wood pulp. This was for Quebec use, and it was wood pulp from Quebec, and it was compared to bagasse from China. And in this case, the expanded polystyrene was performing very well compared to the other ones, or at least comparable also to the wood pulp, and certainly not in the worst ones. Now, the reason why these bans are not necessarily using this LCA-based information is because the problem that they want to address with this ban is actually not captured in LCA. The problem of marine litter from plastics reaching the rivers, the oceans, and then generating eventual impacts on ecosystems, fauna, flora, tourism, etc., which we want to prevent, is not captured in these indicators. So this LCA results then doesn't seem to be appropriate to support this decision, and hence these bans are put forward without having the complete picture, because we were not able to provide this complete picture. Now, what this means is that this little orange box here was missing. The translation between the inventory flows, which I'm guessing you're all probably familiar with, into results in a series of impact categories, about a dozen of them, and then hence the further translation into damages category into these 3 areas of protection, did not include these impacts of plastic flows into the environment, generating potential impacts either via ecotoxicity and human toxicity, so the categories that we already know and use in LCA. So this model here does not yet exist. And this one also capturing the physical effect of this plastic litter, which may not go through a toxicity pathway, but may still impair ecosystems, and we'll see how in a bit. And this can have then potential impacts on human health and ecosystem quality. So this was the main gap in LCA, which originated to the working group MarILCA being founded in 2018 by myself and two colleagues, Professor Jan Vasquez-Rowe in Peru at PUCP and Professor Francesca Verones in Norway at NTNU. And this working group was founded, and indeed, as was mentioned in the introduction, a little bit following the model of WULCA, which was for water use in LCA, founded 10 years before that in 2008, and which fostered and led the development of water use methodologies and leading ultimately with the AWARE methodology as the recommendation. And we wanted to do the same thing and hopefully do it a bit faster than in 10 years, as there was urgent needs of methodologies in order to fill this gap. This was then our goal, to integrate impacts of marine litter and the priority on plastics into LCA. And this group is supported indeed by the Life Cycle Initiative as well as FSLCI. The plan that we set for ourselves when we started was to first start with a framework to put on the table all the different impact pathways that would need to be modeled in order to comprehensively cover the impact pathways associated with, again, marine litter, plastic litter, but ultimately you'll see that this line could not be drawn exactly. So all compartments are included in the framework, and it is applicable for plastics as a first material, but could be used for others as well. And indeed, this framework was submitted in fall 2019 and was published and then came online in 2021. Then following from that, our second phase aimed at coordinating and launching all these different research efforts, concretely meaning master's and PhD projects mostly, and looking for funding, and really opening this group to anyone who was actively working on the field of this modeling, and with the idea of sitting everyone around the same table to optimize our efforts, to coordinate, to learn from each other in order to develop these models faster and in a more harmonized manner. And this led to several publications. I've put, I would say, the five main ones. There are others as well, and you can find the complete references for these on the MarILCA webpage. And all of this was from the beginning aimed to be part of the GLAM working group of the Life Cycle Initiative. For those of you who don't know, it's a research effort led by the Life Cycle Initiative to coordinate and generate harmonized impact assessment models throughout the life cycle community. And we've joined this effort, and we're developing these factors with this in perspective. And we had to also respect the timeline of this project, which meant providing internally to the project the characterization factors by December 2022. And this was done for 2 impact pathways, which I'll show in a moment. The global framework, which was published in the first publication I mentioned, was an AL. It's quite complex. So there's more boxes than that. This is a very simplified version, which we also used on our website here online to show who's involved in what. This list evolves regularly. There's already some new members that should be added here, but it's to give an idea of which impact pathways are more worked on. So here you can see microplastics is much more worked on than nanoplastics. Very few research happening here, mostly because of still lack of data available on this aspect, and some macro research as well happening. Mostly, I would say, the Norway team works more on macro. We work more on micro at Polytechnique. In terms of compartments, we've focused our first effort in the marine compartment, but of course, we cannot completely dissociate that from the other compartments, and we are working on modeling the fate for also the other environmental compartments. There's work going on degradation here, so really the loss of plastics in the environment, on fragmentation, which is really this small arrow here going from macroplastics to microplastics. And then in terms of exposure and effect, most of our efforts is taking place in the ecosystem quality impact category, with some work happening on human health, and as well some work on ecosystem services and eventually socioeconomic assets loss. What I will be, so this is again the same framework, and what I will be focusing the rest of this presentation on is the latest development and the proposal of new characterization factors for this box here, meaning the emissions of microplastics or resulting from the fragmentation of microplastics into the marine environment, leading to impacts on ecosystem quality due to the physical effect, as I mentioned, to be separated from the ecotoxic effect from additives, for example. So if you're familiar with the mechanics of life cycle assessment, you probably know that we assess damage on ecosystem quality by multiplying an emission with a characterization factor. So in this case, we are looking at the characterization of a microplastic emission by a characterization factor, which can give results either in species year or in PDF meter square year. And the inventory can be expected to be found in kilograms of a specific plastic, for example. And we'll come back to that in more details. Characterization factors, traditionally for emission-based categories, are composed of these three sub-factors. So a fate factor, an exposure factor, and an effect factor. And the fate will describe the distribution and the longevity of the microplastics in the subcompartments, the compartments and subcompartments. The exposure factor would quantify, in this case, how much our ecosystem being exposed to the emissions, so microplastics. Here it is via ingestion. And the effect will quantify, in this case, the animal health issues and the reproductive impairment that can be observed associated with a specific exposure of a specific contaminant in a specific compartment. So in case of marine or aquatic ecosystems, the exposure and effect factor can often be combined, or we can assume basically a value of 1 in terms of exposure, which assumes that all the emission that is found in a compartment is available to the ecosystems, meaning that either it is soluble in terms of contaminant, here in terms of microplastics, it can be ingested no matter where it is in the compartment, basically. And hence, this has led to the development of a combined exposure and effect factor. This was done as one of the first publications that I've mentioned in the second phase with this paper, Lavoie, published in 2021, collecting all the ecotox data that could be found, covering in as many species as possible. And again, here focusing on virgin polymer, because the idea was to not include here the potential impacts from additives, leaching, and the ecotox effect, but really focusing therefore on lab studies of virgin polymer. And using this ecotox data and using the HC50, we could derive an exposure and effect factor in this case. And this led to a value of about 73, so potentially affected fractions of species meter cube per kilogram of microplastics in a compartment. And this was including 13 chronic EC50s or LC50s. For those of you who know the details of that, what's important to retain from that is that it was the non-extrapolated values from acute. So we only looked at chronic. And these were using the best data. So when you dig into this paper, you see that there's a few different values depending on how much we were willing to include extrapolated data or not. And in the end, it didn't affect so much the results. So we went with the best data, let's say, which was a bit more limited. And then 2 years later, so in 2022, the work of Lavoie in 2021, of course, was going up until 2020 in terms of data available. 2 years later, in 2022, we were able to update this and add more data, going up to 25 data points and changing the value. And I'm sorry here, this is not the correct value. It's actually down to about 42, if I'm not mistaken. So it's almost divided by half, which may seem like a big difference If you're familiar with Equitox model, a factor of 2 is actually quite a small difference. It's still within the same order of magnitude. And still we were able to test that later on in the uncertainty, as you'll see. But all that to say that additional data was used and integrated, and that it did reduce this factor by 2. And the final value here, you'll see it's in a paper being currently reviewed. So then what was done to model, so this was the exposure and effect factor. The biggest challenge in this modeling is probably the fate modeling, because it includes detail on degradation rates of different polymers in different conditions, the sedimentation rates, also taking into account different environmental conditions, ocean currents, etc. And in terms of pre-fate, we could say the fragmentation of macroplastics to microplastics would also needs to be quantified. All of this was done, well, the fragmentation is done in a very simplified way for now, as there's PhDs working on that currently. Same with the exact sedimentation rates to be modeled in detail, taking into account the ocean models and topography and etc. But still, it could be modeled in a simplified way. And the degradation was modeled in a bit more detail here. In any case, because of the variability of data that can be found regarding adequate sedimentation rate or different degradation rate, there was some ranges always taken into account, whether it was based on scenarios or uncertainty ranges. And for the fragmentation, we went from the lowest fragmentation of 10% of the macroplastic that would fragment up until 100% fragmentation. And you'll see in the case studies, I'll show a large range of uncertainty is among others, due to this large proportion of potential fragmentation here. The degradation rates were modeled in a bit more details, and it's quite described again in an upcoming paper, but it takes existing rates and equations provided by Chamas and develops it further, and specifically for the 9 polymers that we'll be looking at. And sedimentation rate is based on polymer density and adequate rates for specific density of a polymer. And still with that, we have included different rates of fast, medium, and slow for each types of polymer based on the data available. What is interesting to see when we model these fates for 3 different polymers here, going from some of the higher density one, PLA, medium one, and lower density as expanded polystyrene, is the respective effect of degradation rates versus sedimentation rate. So when we look at high density polymers, the rate of degradation doesn't really make a difference in the fate, because the sedimentation happens relatively fast, and this is what will influence the most the fate. And at the other end of the spectrum, the expanded polystyrene will have such a slow sedimentation rate that the rate of degradation will not make a difference, at least for the fast sedimentation rate of the EPS, and even for the medium one here. So it does point towards the need to research better and model better the degradation and the sedimentation aspects and put them in perspective. Yet all of that was taken into account in the elaboration of these characterization factors. So these are the 9 polymers that were modeled. You can see them here, from high density polymers, so tire and road wear particles here at the top, and the other acronyms you probably know, PVC, PET, PLA, and all the way down to expanded polystyrene with the lowest density polymer. And what you see are the units here on the axis are the endpoint characterization factors. There's also midpoint ones, but the graph would look exactly the same in PDF square meter year per kilogram emitted. And you also have here a distinction of 3 different shapes, whether it's film, fiber, and sphere, which not make much of a difference. The size will make more of a difference. This is it's represented by the size of the symbol here, going from the smaller size to larger size. And this was meant to cover the entire range of microplastics sizes. So from 1 micron to 5,000 microns. And for the high density polymers, you see that it doesn't change much actually, because they are high density, they will sediment quicker, and they will be more quickly buried into the sediments and the lower layers, and hence will have factors of lower effects because of a low exposure to ecosystems, a shorter exposure. And when we look into the other ones, then we see that there's more impacts and also more variability and also more uncertainty, specifically when we reach expanded polystyrene, because it's such a light particle, it can remain a very long time in the ocean, and then many things can happen, whether there's currents, etc., and hence the larger variation and also uncertainty for these factors. If we put them in perspective to other types of chemicals that we are assessing in LCA, so this was all the black dots represent all the different chemicals that are assessed in use stocks for marine damages in same units. And you see here where you have the bars are some of the characterization factors for the endpoint emissions that you have just seen of the different polymers. And it ranges a lot. It can be representing as really a low impact substance when it comes to the high density one. And it could be a higher impact when it comes to expanded polystyrene. But with the uncertainty range here, it could really be almost anywhere in the upper part of the curve here or the lower part. So quite some variability here. It shows the importance of distinguishing the type of polymer, because it will influence a lot the potential impacts, and the need for more proper research for degradation and fragmentation as improved human and the ecotox data. But still, we wanted to test those in case studies. And before I show that, I wanted to show here where these factors can be used. So this is a representation of the Plastic Leak project, which are proposing a framework for assessing the emissions, so really the inventory part of different types of microplastics emerging from different sources and being emitted into different compartments. The factors that you have seen are for emissions into the ocean, but in terms of preliminary emission, this emission can take place either directly into the ocean, but we wanted to include also a way to use those when the microplastics are emitted in fresh water. So we have used their rate here of, let's say, redistribution for an emission that takes place into fresh water, how much of it will be released to the ocean. And this is a rate of 70%. So assessing that 30% of microplastics emitted in freshwater will sediment in the freshwater sediments of the river sediments, and 70% will be flushed to the ocean. So with this, we have for now also suggested to use these factors with this same 70%. So moving on to the case studies, the red circles here show you which polymers were tested in the following case studies. And again, so these factors are now in a publication that's under review in the Journal of Cleaner Production. This is for the characterization factors and also the methodology for these case studies. And these case studies were done in addition in a collaboration with UN Environment and Life Cycle Initiative for the very recently launched report on supermarket food packaging and their alternatives. This was launched at the LCA Food in Peru in last October. And in this, where they really go into details into which the different types of food packaging, we were able to apply our characterization factors for 3 of the case studies because there was enough data from the inventory perspective and it was modeled in the proper way where we could just come and add the impacts of the emissions of microplastics, including those from fragmented microplastics, into the results of an LCA. So the first one is the same to-go food container that I've showed you at the beginning, because that's a study that we actually did at CIRAIG, so it was easy to have access to the data and compare these 3 food containers. Then there was a PLA versus polypropylene lettuce bag that came from a study from Vigil et al. In 2020. And the last one was reusable fruit crates either in polypropylene or HDPE, and this was compared with a cardboard box. And it came from a study from Abejon et al. 2020. And again, what was done here was really to take the results of their LCA, take the inventory data that was available, or sometimes exchanging with the authors, and apply our factors to see how much or if the results would change once we add the factors and the impacts of the plastics emissions in the marine environment. For the inventory, because as you probably know, we don't have any inventory data yet in the databases, we were based mostly on the Plastic Leak project, which really provides guidelines and values for the quantification of the plastics emissions. So there was a release of primary microplastic pellets at the production stage. And again, this ratio of 70% of emissions that are emitted to freshwater being transported to marine water. Then there was secondary microplastics from the microplastics lead at the end of life stage. So what we think the most about what we see are really the bag or the food container being emitted into the environment and how this will fragment into microplastics. The emission of the microplastics, so the food container or the bag, is modeled again based on the Plastic Leak project guidelines. It will differ based on the economic level of the region, assessing different level of waste management. It will also be influenced by the weight of the object and its propensity to be transported by wind, and the residual value identified. Much less chance of someone picking up a lettuce bag to go resell it than a reusable crate out of plastics, which can be used and serve a purpose, and if it ends up in the environment. And again, still using this modeling, different fragmentation scenario were tested, as I mentioned, from 10, 50 to 100%. And the tire and road wear particle released from tire abrasion is only relevant, of course, for the transportation stage, and was only tested for the first case study, the food container one, because it's the one we realized and we had integrated that from the beginning. But what we can see is that in general, this was much less in terms of quantity compared to the other microplastic sources. So what could be seen from that? Well, for the reusable crates, you can see here the impacts in polypropylene, HDPE versus the cardboard box. The beige part here being global warming potential impacts. And the dark brown box is these additional impacts from the physical effects on biota. And in this case, we have used the worst case terms of potential emission into the environment. But as you can see, we don't really see a brown part here of the column. And that is not so surprising because a cardboard, a food crate like that has a high residual value, is quite heavy. It's quite a small leakage into the environment. So not much additional impact here from impact on biota from this one. The lettuce bag here, again, is compared to polypropylene and the polylactic acid. I apologize for the line here. And the additional impact from physical effect on biota, again, showing the worst case, is the small purple line here. So again, not a very large impact here compared to the rest, and mostly, again, to climate change impact on ecosystem that are coming from this lettuce bag ending up potentially in the environment. Now, are we doing that all for nothing? No, this is already an interesting result and provides guidelines, and it can also provide very different results if we have a different polymers. And in the food container case study that I showed you at the beginning, where we had bagasse wood pulp and expanded polystyrene, the part in gray here that you see being added to the result actually shows this additional impacts of the expanded polystyrene being released into the environment and fragmented into microplastics. The solid gray line shows this one here, physical effect on biota, 50% expanded polystyrene fragmentation rate, so 50% fragmentation of the microplastics with an average case characterization factor, which means average degradation rate and average sedimentation. And when you look at the squared, the gray squared part here, I guess you don't actually see my mouse. Maybe now you will see it better. So this part here, this is where we have taken still 50% fragmentation with the worst case characterization factor. So in this case, it would mean slow sedimentation and slow degradation. And if we look at the total added impacts here, is if we take 100% fragmentation rate, fragmentation with the worst case characterization factors. So here we see that it actually has the potential of greatly affecting the conclusion of this study. And as you remember from the characterization factor, the expanded polystyrene was indeed the one with the worst one, and also with the largest uncertainty. So up until now, in the case studies tested, only here the worst case expanded polystyrene seemed to potentially influence the conclusion because of its low density and slow degradation. And to the other tests done, the contribution of the plastics emissions in the environment was negligible. However, only the microplastics impacts in the oceans were considered here. So the microplastics effect of the bag, for example, was not yet considered. The factors were just finalized last December, and we haven't had a chance to test them yet. And also none of the toxicity potential effects of the additives were integrated, as well as the invasive species, as well as socioeconomic assets, etc. So this is similarly the same conclusion from these case studies, still more impact pathways to be included. Still, most single-use alternatives to single-use plastics seems to perform worse than the single-use plastic item itself. This doesn't mean that we can just use plastic and throw it out and leave it in the environment, but I think it raises a very relevant flag for this hot trend of developing single-use alternatives to plastic. Multi-use is always a better approach, and even then it's important to look in detail at the impacts behind, and not just because it's not single-use plastic, it will be a better option. And also, global warming remains the most important impact category for ecosystem quality damages in the case studies looked at. So that's it from my side in terms of conclusion. So we are now proposing and under review our characterization factors for 9 polymers, 3 shapes, and 5 sizes, with, of course, default ones being pointed out if you don't have all this detailed information. The fate of high-density microplastics shows that the sedimentation is much more important than the degradation. But for low-density microplastics, there's still high uncertainty regarding the fate. The paper is under review in the cleaner production, and it will be proposed for the GLAM recommendations, which are to be finalized by this summer. And in terms of next steps, there's still quite some work to come in terms of the detailed sedimentation and fragmentation modeling, which are currently underway, and human health impact pathway also to be more delved into.
Thank you so much, Professor Boulay. Thank you so much to consider, and thank you so much for all the hard work you're putting into this. Right now, one of our sustainability analysts from EarthShift Global, Miguel Hernandez, will ask the questions from the audience.
Thank you, Holly, and once again, thank you, Professor Boulay, for this very interesting talk. We have a couple of questions from the audience. The first one is, from the research you've done, would you expect the microplastics to have the marine environment to have the most ecosystem damage of all the different pathways, or are there other pathways that could have higher impacts?
That's a very good question. I'm assuming we're talking about the pathways specifically associated with plastics being released. I guess what we don't yet know would be the one of the additives of ecotox. If there would be one that I would be unsure of, it would be between this one. And we haven't looked into the microplastics, but I think the microplastics impacts in general, again, it's my expectation. We haven't tested it, but I think that will be lower. The ecotox effect associated with the additives, which will be much more complex because additives will vary a lot from one polymer to another, and sometimes there will be several additives, and then contacts with heavy metals, which can also transport or increase the amount of ingestion of other contaminants. So if we go into this kinds of ripple effect, that could be significant. So in my view, it will be between these two.
Okay, thank you. There's another one related to the conclusions. Is the assumptions that sedimented material doesn't have much impact a final conclusion, or something that needs to be revisited?
Well, yeah, very good point. And I didn't go into the details because there's a sedimentation, which is on the first top layer of what we are proposing is 12 centimeters. It's not completely removed from the environment at this point, and it gets resuspended, and there's ecosystems that depend on this layer. Once it is what is called deeply buried, below 12 centimeters, we don't really know what kind of effect could take place there and what kind of data we would need to assess the effect of microplastics being in that part. So I think for now, we will go for no effect below 12 centimeters. Of course, all hypotheses are always to be assessed in the future if more information comes in. But for the 12 centimeters of the top part, this is definitely not a zero value. It's not completed yet, and it's part of the PhD of Carla Hajar, who's modeling in detail the fate of the microplastics only within the marine compartments and all the subcompartments.
Okay, thank you. Here's another one. What are your thoughts on the impacts of marine biodegradable materials?
We are looking into that. What is still to be seen is the rate of biodegradation of these materials. It seems that sometimes something can be biodegradable according to some standards, which are in conditions that do not reflect the marine conditions. Something can be biodegradable at 20 or 30 degrees or more, and with high aerobic conditions, which does not reflect the marine environment, which can be more at 4 or 5 degrees and with much less oxygen. So this is still something that we're looking at to dig into the most accurate degradation rate of these so-called biodegradable materials. Some seems to biodegrade indeed faster than others. And then we will be able to develop some characterization factors like this by adapting the degradation rate, and the rest will actually remain the same. Once we know that it's a faster degradation, we can assess and compare it and see really if it makes much of a difference.
Okay, thank you. Here's another one. You mentioned that nanoparticulate plastics were not included under consideration due to lack of data. Based on your findings, do you think that nanoparticulate plastics may not be as impactful as feared?
Actually, indeed, I said it was not included. It's not entirely true. The effect factor data that was used to derive the effect factor, so the HC50, was often for micro and nanoparticles. So the effect factor is applicable to nanoplastics. So the effect will be quite similar because we were not able to distinguish it often because of the range of sizes. Sometimes it's at the limits, sometimes it was several different sizes being tested. What we don't yet have information on is, or we didn't model in details, was the degradation, the sedimentation, so the rest of the characterization factors. So no, I wouldn't say that they're less impactful. And in terms of effect, I think they could be quite comparable. Of course, they will degrade faster because they're smaller. But no, I wouldn't be ready to conclude that yet.
Okay, thank you. From a practical perspective, are these factors already available for use?
They're not publicly available because the publication is not yet finalized. But on a case by case, if you want just the Excel file to play around with the factors, even though you cannot officially refer to a publication, you can contact me and we can have an exchange on that. That's not a problem.
Okay, here's another one. When we do LCA for plastics and we compare them with other alternatives such as bioplastics, what are the most important environmental indicators?
Well, what we've seen in terms of result in the case study that we've done was global warming coming up as the main causes of impacts at the endpoint level. Now, I'm not sure if in this case the alcohol indicators refer to midpoint indicators. I think global warming is definitely the one that is important and will fluctuate a lot between different alternatives, and we tend to turn a blind eye on because we will focus on the biodegradability or on the recyclability, but the upstream of the life cycle is quite important. Of course, being a life cycle assessment researcher, for me, there's not a specific choice of indicators that should be made. They should all be looked at, because if we don't do that, then this is where we lose our reason of existing by saying you need to look at everything, the entire pathway, the entire pathways, and also the entire life cycle.
Thank you very much. What are the plans for this initiative to begin to consider the impacts of common additives that have been neglected for now?
So there's some work already occurring on this. There was a first master that was done in one of the papers I listed. We're starting to touch on this topic, Yibo and Al 2021. And now there's a current PhD student also working on that in Portugal, looking at how to map out the main additives and the models that we already have and how we can integrate this. So maybe I would give it another year or two, and then hopefully we'll be a bit more solid in this way.
Thank you. And also regarding characterization factors, have you applied your characterization factors to materials intentionally used in marine environments like fishing nets or things like that?
Not yet. Not yet. This is really, when I'm presenting to you, are really, really fresh results. We couldn't squeeze in more between the time they were developed in this webinar, pretty much. But we're open to disseminating them so that they can be used in case study, to testing them, to collaborating with anyone who would like to apply them.
Okay. I think you already partially answered this, but what work is planned next in your projects around this initiative?
So in terms of these factors for microplastics emissions, concretely, it will be finalizing the operationalization, the recommendation via GLAM. So this project with Life Cycle Initiative, along with the microplastics recommendation as well, that is included in the GLAM recommendation. And on the other side, continuing the deeper work. Human health impact pathway is one of the priority one, which I'm actually currently recruiting a student for, in case there's anyone here interested. And there's also ongoing work already started, which will be crucial to complement this model on the fragmentation, on the sedimentation with the fate in the different subcompartments. And I would say these are the top priorities, and as well the additives from the members of the group, as I mentioned.
Thank you. I think we have time for one last question. There is still a lack of internationally agreed microplastic analysis methods. The majority of the studies still express their results in terms of particle number concentrations instead of mass concentrations. Do you know of any recent developments on microplastics analysis methods?
Not being one in the lab doing the measures, I'm not the most connected with this, but however, I think I can perhaps point you towards a publication which was also the result of MarILCA working group collaboration, Pauna and Al 2022. It's also referred to on the MarILCA webpage. And this is a collaboration between, I think we are 10 co-authors, 5 for the more LCA modelers world like myself, and 5 from the ecotox world, and we have had this conversation on how data should best be reported to be useful for LCA modelers, and what crucial information, if it's missing, makes it unable for us to use it, whereas maybe for the ecotoxicologist, it's not a big deal to add, and indeed what kind of units will be the most useful. So we've tried to send out this message to make it the most useful, make their effort the most useful possible for the LCA community. It was only published a few months ago, so I doubt that they would have had yet a huge impact on changing the practices, but hopefully this will come.
Oh, and we have one last question. What inventory data can be used to apply these factors?
Well, there's no systematic data set yet included in EcoInvent to apply that, but the Plastic League guidelines is really the guidelines that we have set ourselves to from the beginning to be aligned with, so that as they generate data, guidelines, recommendation, we can directly use our factors with the methodologies that they put forward. And now it's moved into a plastic footprint network, which will develop further the methodology. So our goal was really from the beginning to separate our mandates so that they can better do theirs and we can better do ours, and yet stay informed so that their data can be used with our methods.
Okay, I think that's all the questions. So thank you again, Professor Boulay, for such an interesting talk and answering all these questions. And thank you all for joining, and we hope to see you soon in our next session.
Thank you very much.